let's take a look at an example that uses Newton's method to approximate the zero of a function. Here we're asked to assume that x of 1 is equal to 2, to find a third approximation, x of 3, of the zero of the function x cubed minus 2x minus 5. Now in this case, they tell us what x of 1 is. They tell us to consider that x of 1 is equal to 2. Now this is so that the assumption is that x of 1 equal to 2 is a good approximation to the zero of the function. Sometimes you're not given this value and you have to look at a graph of a function to pick an educated guess to where to start from. In this case, we have that x of 1 is equal to 2, and we'll use it to develop up to x of 3. To compute x of 2, we'll take our previous value x of 1 and subtract the quotient f of x1 divided by f prime at x1. In this case, we need the derivative, so let's write the derivative down here. So f prime of x from this cubic function is 3x squared minus 2. So here we'll have our 2 minus f of 2 divided by f prime of 2. So this would be 2 minus my function f at 2 would be 2 to the third minus 2 times 2 minus 5 divided by my f prime of 2, that would be 3 2 squared minus 2. And in computing this out, we get exactly 2.1. Now we'll use this value to compute x of 3. X of 3 again would be our previous value minus the quotient f at x of 2 divided by f prime at x of 2. So this would be 2.1 minus f at 2.1 divided by f prime at 2.1, which can be computed as 2.1 minus 2.1 cubed minus 2 times 2.1 minus 5, all divided by f prime at 2.1, so 3 times 2.1 squared minus 2. And we compute this value. We don't get the exact value, we get an approximate value. We get approximately 2.094568,121. Now, this is the value that my calculator is giving me. And there might be a whole lot of numbers following after that. When going through Newton's method, I suggest you write all of these numbers that are given to you by the calculator, because the calculator is really trying to give you, or this method, Newton's method, is really trying to give you the best approximation to the zero. And in these problems, these decimal places do matter. In this case, we're done. The approximation x of 3 is approximately this number. If you want a better approximation to the zero, you can repeat the process and get x of 4, x of 5, and so on and so forth. I want to do a few more iterations so you can kind of get to see what happens when these x of n's start converging to a specific value. So if we repeat the process for x of 4, we would get approximately 2.0945. Notice that these digits match up with my x of 3, but then I get 51482. There was a change between my x of 3 and my x of 4. As soon as I see that there's a change, I'm inclined to consider doing another iteration to see if I can get an even better approximation. If I compute my x of 5, I get approximately 2.094551,482. Notice that between x of 4 and x of 5, there were no changes. This means that my calculator has reached its limit, and this is the best approximation it could give me for the zero of my function, 2.094551482. Let's take a look at the graph of my function and see if this is reasonable. Again, remember the root is approximately 2.09 from this method. So here's my function, x cubed minus 2x minus 5. And if I turn that on, it's a cubic function. And if I zoom in really close to where my graph intersects the x-axis, my graph intersects approximately there at 2.0946. That's really close to my approximation, but my approximation is better. This decimals interface only gives you 4 decimal places here, while I gave you 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places, right? So Newton's method can be very powerful.